The number of spinal fusions performed each year in the United States is predicted to reach 876,000 by 2022. However, independent research by spinal surgeons has shown that the current failure rate for spinal fusions is 17%, which will result in 149,000 failed fusions and 92,000 revision surgeries per year. A failed fusion is often associated with the presence of scar tissue at the intended site of bony repair, rather than mature bone. The body's natural response to surgery is the upregulation of macrophages. The pro-inflammatory M1 phenotype is responsible for promoting fibroblast proliferation, fibrous tissue formation, and in sites of chronic inflammation, the development of scar tissue. The pro-healing M2 phenotype associated with the later stages of wound repair and tissue remodeling are anti-inflammatory. M2 macrophages upregulate mesenchymal stem cells both directly and indirectly, leading to the formation of new bone. Immediately following spinal fusion surgery, the undifferentiated macrophage population will respond predominantly with the M1 scar tissue forming phenotype during a phase of acute inflammation. After this key juncture, inflammation and proliferation of M1 at the expense of the M2 phenotype will result in fibrous tissue formation, ultimately causing the fusion to fail. However, if the M2 phenotype becomes dominant, bone formation will occur, resulting in a successful outcome. Kuros Biosciences have developed MagnetOs granules, a bone graft with a unique submicron surface topography. MagnetOs granules are available in a moldable putty, allowing the surgeon to sculpt the graft accurately to bony defects. Once implanted, the polymeric binder is rapidly resorbed, leaving the granules in place to take effect. MagnetOs granules are designed to mimic the porous trabecular structure of cancellous bone. Unlike first-generation bone grafts with conventional surface architecture, the advanced surface of MagnetOs has needle-shaped features that are submicron in size and ideal for the attachment and spreading of macrophages. When the patient's macrophages are exposed to the submicron surface topography of MagnetOs, they are reliably polarized to the M2 phenotype. Macrophages of the M2 phenotype have been shown to perform several functions in bone. They remove debris from sites of bone repair and restore the extracellular matrix by promoting secretion of collagen by osteoblasts. Cellular signaling results in mesenchymal stem cells being freed from the surrounding tissues and being drawn to the submicron surface of MagnetOs. Here, they attach and differentiate to osteoprogenitor cells. Signaling also results in mesenchymal stem cells being recruited from the infiltrating vascular system. M2 macrophages have been shown to express BMP2 and crosstalk with stem cells via the prostaglandin PGE2 pathway. The recruited progenitor cells in turn differentiate to osteoblasts. These cells then begin the work of laying down collagen that will soon mineralize to form new bone. Unlike conventional osteoconductive bone grafts, for which there is a greater risk of fibrous tissue formation and scarring, bone formation takes place throughout MagnetOs simultaneously, without the need for added cells or growth factors, resulting in a uniform, solid, stable, and reliable fusion that is equivalent to the gold standard of autograft.